You put an item on the counter. A scanner passes over a group of black and white stripes. A beep. A price appears. It feels instant and almost magical. But that beep is the end of a quiet conversation between light and pattern. Today we're going to decode that conversation, how barcodes turn ink into identity. First, a very short history. The idea of encoding information in patterns goes back a long way. But the barcode as we know it started in the late 1940s. Two engineers, Bernard Silver and Norman Woodland, sketched the first design. They filed a patent in 1952. The original concept was even inspired by Morse code and used concentric circles. Fast forward to the 1970s. IBM engineer George Laurer developed the Universal Product Code, or UPC, and the first supermarket scan of a UPC happened in 1974. From there, barcodes spread through retail, warehouses, and shipping, because they solved a hard problem: how to cheaply and reliably identify items at scale. So what is a barcode, really? At its simplest, a barcode is a visual representation of data, a sequence of bars and spaces that encode numbers or letters. But beneath that simple surface are a few important rules that make barcodes reliable. Let's look at a common example: the UPC-A barcode used on many products in the United States. A UPC-A holds 12 digits. Those digits are arranged like this: 1 number system digit, 5 manufacturer digits, 5 product digits, and 1 check digit. The barcode itself is built from repeating patterns of narrow and wide bars and spaces. The smallest unit in the pattern is called a module. Each bar or space is an integer multiple of that module width. A UPC barcode divides into 3 main parts: a start guard pattern, a middle guard pattern, and an end guard pattern. These guard patterns are special bar space patterns that tell the scanner where the code begins, where the left half ends and the right half begins, and where the code ends. They also help the scanner determine orientation and timing. The left and right halves of the UPC are encoded differently. That asymmetry helps the reader know whether the code is upside down. On the left side, digits are encoded using one set of patterns. On the right side, digits use a mirrored set. When a scanner reads those patterns, it checks for the guard bars and then reads the widths of bars and spaces across each digit slot. Now the check digit. The last digit in a UPC is not arbitrary. It's a simple error detection number computed from the previous digits. The typical calculation goes like this: add the digits in the odd positions and multiply that sum by 3. Then add the digits in the even positions. Add those two totals together, and the check digit is whatever number brings that final sum up to the next multiple of 10. This catches common mistakes like a single wrong digit or 2 digits swapped, so a misread will usually be rejected. How does the scanner actually see the code? There are 2 common approaches. The classic barcode scanner uses a red laser beam that sweeps across the bars. Black absorbs light, white reflects it. A photodiode measures the reflected light as the laser moves across the code. The output is an analog waveform of high and low reflections that correspond to white and black. The scanner converts those reflections into a sequence of timings, how long the beam saw dark versus light, and translates those timings into module widths and then into digits. The guard patterns and parity checks validate the read. More recently, camera-based imagers and smartphone cameras have become common. These devices take a snapshot of the barcode and use software to analyze the image. The software converts the image into grayscale, finds the quiet zone, the core margin before the bars start, locates the guard patterns, and samples across the bars to measure widths. This method is what reads QR codes and other 2D symbologies as well. A quick note on the quiet zone: it's the empty margin on each side of the barcode. If it's missing or too narrow, many scanners can't tell where the code starts and stops, and the read fails. So that blank space is as important as the bars themselves. Why do barcodes sometimes fail? The usual culprits are low contrast, smudges, reflections on glossy packaging, too small or too large printing, or printing at the wrong resolution, so the module widths are imprecise. Damage to the guard bars is particularly bad because those patterns are the scanner's anchor points. Not all barcodes are 1D stripes. 2-dimensional barcodes, like QR codes, store information across both dimensions. Instead of varying bar widths, a QR code uses a grid of square modules. It has finder patterns in 3 corners, so a camera can detect orientation. and it uses error correction, typically Reed-Solomon codes, so the code can still be read even if part of it is obscured or damaged. That makes 2D codes denser and more robust for certain uses: links, tickets, payment, and IDs. Where are barcodes used? Everywhere. Retail checkout, warehouse inventory, shipping labels, boarding passes, medical records, and manufacturing lines. The same principles scale. A reliable, machine-readable ID printed on an object makes tracking and automation practical. Let me give you one small example of how things come together in one scan. The scanner sweeps a laser. The photodiode records a waveform. The reader locates the start guard, times the dark and light bands to determine module widths, decodes each group of modules into digits, computes the check digit, and validates it. Then sends the product code to the point-of-sale system, which looks up the price. All of that in a fraction of a second. Here's the core idea to take away. A barcode is a compact, error-checked binary language. Bars and spaces are just binary states, dark and light. The structure, modules, guard patterns, parity, and a check digit, turns that raw pattern into reliable data that machines can read at scale. That clever combination of simplicity and rules is why barcodes remain one of the most successful data formats in the world. If you enjoyed learning the tiny engineering behind everyday tech, subscribe to Explain Engine for more quick, clear breakdowns. But most importantly, next time you hear that beep at the checkout, you'll know you just witnessed a small, elegant translation, ink and light into identity. That's it, the secret language behind every scan.